Welcome, Ichak solution. This is vector 2, equation of a plane in 3 dimension. So if you haven't watched the videos on vector 2 on the previous lessons, I would encourage you to go and look for those videos so that you can see the progression of the lessons. Alright, so in this case we are going to start by defining a plane. Alright, so a plane is an infinite flat surface in 3D space which is described by an equation with infinite points and infinite lines. Alright, so let's see how it looks like on the 3D space here. Alright, so this is a typical example of a plane here. Alright, so you can see on this plane, what are we expecting? We are expecting to see several points that will be on the plane. Several points that will be on the plane, and also we're expecting to see infinite lines that will be on the plane here. Alright, so let's derive the equation here. So let's assume that we have a general point that we have which is in the plane here with a position vector r here. So moving from the origin to a position vector r, so you can move from the origin to a fixed point A, and also move from A to r here. That's the first thing that we can do. But r cannot be the position vector only that will be in the plane here. There will be other general points that will be in the plane. So let's say we have maybe another position vector which is r1 here, which is in the plane. So moving from the origin to r1 here, we can move from the origin to a fixed point A here, and also move from A to r1 here. So you can see now we have two vectors that we can have that can be also lines. We have AR and AR1 here, and also I have a point that is in the plane here. So by vector cross product, we know that the cross of AR and the AR1 will just give us the normal vector here. Right, so the normal vector here is going to be perpendicular to the plane here. So it's not always the normal vector will be on the fixed point or on the coming from the fixed point. So the normal vector can be anywhere in the plane here. So any two vectors which are non-parallel, which are lying in the plane, if you cross them, they'll give you a normal vector here. Alright, so now we can now write the equation of the plane. So we have the scalar product form, which is the first form of the that I'm going to write here. Alright, so you can see now AR dot the normal vector should be equals to 0. AR moving from point A to R here dot the normal vector should be equals to 0, because vector AR and the normal vector are perpendicular to each other, so they give us a 0 here. But what do we know? We know that AR is R minus A dot what? The normal vector should be equals to 0 here. So this one is now the scalar product form here. Alright. Then we have the vector form. So the vector form, we are just continuing from the scalar product form here. So you can see here the dot product here is distributive over addition and subtraction here. So we can now distribute the normal here under the dot product here. So it's going to give us r dot the normal minus a dot the normal equals to 0 here. This is the vector form. So if you try to simplify this one, this is going to give you r dot normal is equals to a dot normal here, which is r dot normal is equals to d here, because a dot normal will give you a certain value that will be equals to d here. So how do you find the equation of a plane? So to find the equation of a plane, we have requirements that I've just stated here. Alright, so the first requirement, number one, you need the fixed point on the plane, and also need the normal vector to the plane here. So these are the general requirements that you need to find the equation of a plane. Number one, you need the fixed point on the plane and the normal vector on the plane here. Alright, so let's go to the example here that we have on the equation of the planes here. Alright, so you can see they are saying find the vector equation of the plane pi, which contain the point A is equals to 2i minus 3j plus 3k and is perpendicular to B is equals to 3i minus j plus 2k, and prove that the point P with this point lies on the plane pi, and write the plane in Cartesian form. Alright, so a plane can be represented by pi. Alright, so that's what you need to know here. A plane can also be represented by pi here. Alright, so let's try to draw the diagram here so that you can see how it look like on the diagram here. Alright, so this is our plane that we have, and this is the normal vector which is perpendicular to the plane. So the normal vector here, you can see it's a vector perpendicular to the plane, which is 3 minus 1, 2 here, 3 minus 1, 2 here. So this is vector B perpendicular to the plane. And also we have a fixed point which is in the plane, which is 2 minus 3, 3 here. So as long as we have the fixed point in the plane and the normal vector perpendicular to the plane, we can find the equation of the plane by applying r dot the normal vector is equals to a dot the normal vector, where a is the fixed point in the plane and the n is the normal vector here. So that's what we are going to use here. So a, our fixed point, is 2 minus 3, 3 here. Then the normal vector is 3 minus 1 minus 2 here. So now we apply here r dot 3 minus 1 minus 2, which is equals to the normal vector, the fixed point here, dot the normal vector here. Alright, so this is going to give us r dot 3 minus 1 minus 2 here. So here is the dot product. So it's 2 times 3 plus minus 3 times minus 1 here, plus 3 times minus 2. So this will give us 3 here. So now this is the vector equation of the plane pi here. Alright, then part 2 here, they are now saying prove that the point lies on the plane here. So to prove that the point lies on the plane, we just need to test for the consistence of this point. So we substitute the point on r here. R is just the general point, which is x, y, z here. So we are putting our point 0, minus 5, 1 here into the plane. Then we perform the dot product. So we are going to have 0 by 3 here is 0, then minus 5 by minus 1, which is 5, then 1 by minus 2 here, which is minus 2. Then we simplify here, we're going to have 3 is equals to 3. So you can see the left hand side is equals to the right hand side. So which means the point 0 minus 5 1 lies on the plane here. Alright, then number 2, they are now saying write the plane in Cartesian form. Alright, so to write the plane in Cartesian form, we are just writing our plane in the form of x, y, z here. That's the Cartesian form. Alright, so we know that r is being represented by x, y, z, the general point that will be on the plane. So just say x, y, z here. Then we are going to perform the dot product here. So we are going to see, we are going to have 3x minus y minus 2z is equals to 3. So this one is the Cartesian equation of the plane here. Alright, so clearly you can see that the coefficient of x, y, z here is the normal of the what? Of the plane. So if I'm given a plane which is ax plus by plus cz is equals to z, so I can just extract the normal here. So the normal will be equals to a, b, c here, the coefficient of x, y, and z here. So that will be the normal vector. Alright, so let's go to the next example here. Find the equation of the plane which contains vector AB and AC, given that the position vector of A is equals to 3i minus j and 2k here. So let's see how it looks like on the diagram here. Alright, so we have vector AB and vector AC that we have here. So this is vector AB and this is our vector AC. Alright, so generally we know that if you do the cross of AB and AC here, this will give us the normal vector. So the normal vector here is a vector perpendicular to the plane here, because it's perpendicular to AC and it's also perpendicular to AB here. And remember, AB and AC will be the vector which are in the plane here. So we are going to perform the cross product here to find the normal vector. So the cross product, we just say IJK and place the first vector AB here and AC. Then our normal vector here is going to be, we close the component of I, then we write this value here, then the component of J with a minus here, then we have this value, then component of K, we close the row and column, then we have this part here. So this will give us the normal vector of minus 6I plus 4K here. That will be the normal vector. So now to find the equation of a plane, we now have the normal vector and we need a fixed point in the plane. So we are going to take A as our fixed point here. So using R dot normal is equals to A dot normal, we are going to have R dot the normal vector is equals to the fixed point dot the normal vector here. So this is going to give us R dot the normal vector is equals to minus 10 here. Remember, this is the dot product here. 3 by minus 6 plus minus 1 times 0 plus 2 times 4 here, which is minus 10. So this is the vector equation here. Alright, so now you can try these questions and the solutions are below here. Alright, so feel free to contact me if you meet any challenges. I will help you. Alright, so see you in the next lesson. Thank you for watching the video.